Unit 2, Lesson 1, Piggy Banks and Pools. We're going to learn the difference between discrete and continuous in this lesson, and we're also going to make a change from Unit 1. We're going to start our counting and our graphs at 0 rather than 1. And we'll explain as we go through this. So question number 1 talks about a little girl, Savannah. She's 3 years old. She has a piggy bank. She wants to fill it. She starts with 5 pennies, and each day when I, which is I guess the big brother or the big sister, I am excited, well, she's excited when I give her 3 pennies left over from my lunch money. Use a table, a graph, and an equation to create a mathematical model for the number of pennies in the piggy bank on day n. So remember, a model is simply when we take mathematics and we apply it to the real world. Now, why would we start this count at 0? Well, for one thing, it doesn't say that on the first day she received 5 pennies. We don't know when she received 5 pennies. The point is, when the problem starts, she already has it. And when we say start, think about a race. We usually start a race at 0. So we're going to go 0, 5 for the first line, and then 1 day later, she's going to get 3 pennies. So imagine 05 might be the night before or the afternoon before. Maybe it's a Sunday, and you say to Savannah, okay, after lunch tomorrow, I'm going to save my change, my 3 pennies. I'm going to give it to you when I come home. So now, at the end of the first day, she's got her 8 pennies. And then 11, and so on. So this is obviously arithmetic. We're adding 3 each time. And so when we look at the graph, and the graph scale, since we only have to go up to 11, that means we could go just every other line. So 2, 4, 6, 8, 10, 12. And so our first dot is on 0 and 5. That's right on the axis. 1, 8. Oops, missed it. And 2, 11. It will form a straight line, as we've said before in our previous unit. And our equation is f of n equals, starting at 5, adding 3. But now, since we didn't start at 1, we can simply call this n. So if you look at the table, we can make that work because it's 3 times 0, which is 0, and then there's the 5. And then 3 times 1, we'll add a single 3. And then 3 times 2, we'll add 3 twice. Let's look at the next problem. So that's the piggy bank. Now we have the swimming pool. So our family has a swimming pool, and it holds 1,500 gallons of water. You decide to fill the pool for the summer. Getting bored of just standing there watching the water flow, you begin to think about a model, a mathematical model, for the time it takes to fill the pool. And so while waiting, okay, let's check the flow on the hose. We find it's flowing at a rate of 2 gallons a minute. That's important. And you have 5 gallons of water in the pool when you started the timer. So see, that's a timer. And timers usually start at 0. Use a table, a graph, and an equation. And notice we're going to model with the variable t. Let me see, did I miss that in the last problem? No, it did say n. Okay, so we're just going to try some different variable names today. T, and that would make this f of t. So if we go 0, 1, 2, It takes at least 3 points to make a pattern. So that's why I'm at least going with 3 lines on the table. 0 would be 5, 1 would be 7, 2 would be 9. We're going up by 2. And then we can simply go by 2 again. 2, 4, 6, 8, 10, 12. And now for our points, 0, 5, right on the axis. 1, 7. Oops. Right about here. And 2, 9. Now, question. Would it make sense to fill in or draw a line between the dots? Well, think back to this problem, our penny problem. Did she receive money in between day 1 and day 2? No, she got the 3 cents all at once. Was the water flowing between minute 1 and minute 2? Yes, it was. So we're going to fill in and draw a line. And I put the arrow just because it's going to continue going in that direction. It will eventually stop, of course, when the pool gets full. So I'm not really saying that it goes on forever, but it certainly goes on past the edge of this graph. Our equation. F of t is, it starts at 5 and it goes up by 2 every second or minute, and t is in minutes. Okay, so now we've got a little bit different idea here in number 3. We're going to go geometric. So it says, I'm more sophisticated than my little sister, so I've saved money in a bank account, pays me 3% interest. So from the last unit, remember that when you have 3%, as a multiplier, that's going to be 1.03. It's 100% plus 3% more. This time, they'd like us to use the letter M. And 3%, of course, is important, and so is $50. So at time M, then F of M will be the money after the month. Again, this one makes sense to start at 0 because when you put in your money, you haven't received any interest yet. So you've received 0 interest. It's 50 plus 0, or 50 plus 1.03, 0 times. Okay, and then 1, and then 2. So we'll take our calculator, and we'll do 50 times 1.03. And that gives us 51.5. So $51.50, and then do it one more time. Take 51.5, multiply it by 1.03, and you get 53.045. Of course, you would want to round that. If you're dealing with money, this 4 would change to a 5, so it's $53.05. Okay, so our scale can change now a little bit. For example, we don't necessarily want to start at 0 on the y, so we could start at 50 and have a little break here. And then we only have to get up to a couple dollars more, so how about we do every square is worth a quarter. So 1, 2, 3, 4, there's $51. 1, 2, 3, 4, $52, and 1, 2, 3, 4, $53. So our dots will go, we're going to start at 50. 1 will be 51.5. And 2 will be 53.045. 0.05, so just a little past 53. Is this a straight line? The answer is no, it's not. But it looks like a straight line. That's because we're zoomed in too far. If you zoom out, like for example, if you put this in Desmos and you zoom out on the function, it's going to look like this. It's definitely going to curve. Okay, but another question, would it make sense to connect the dots together? Well, how do banks work? Banks do not pay you interest every day. When you get a bank statement, it's a piece of paper, and it says basically one day you didn't have the interest on your account, and the next day they paid it. So you get the money pretty much instantly. So it does not make sense here to connect together. The function would be, and it's geometric, start at 50, multiply by 1.03, and take it to the n power. Again, we can say n instead of n minus 1 because we are starting at 0. Last one. At the end of the summer, I decided to drain the 1,500-gallon swimming pool. I noticed it drains faster when there's more water in the pool. That's because of the effect of gravity. That was interesting to me, so I decided to measure the rate at which it drains. I found that 3% was draining out of the pool every minute. And then we're going to create a model. Okay, so before we do anything else, let's look at this 3%. So think about maybe like a pie chart. And there's 100%. And we're going to take off 3% because over and over again, it says drain. We're draining, we're draining, we're draining. So drain takes off what was there. Well, here, I'm going to exaggerate the size. Here's 3%. We're removing that. How much is left, though? 97% has to be left so that it adds up to 100%. That means our multiplier is 0.97. Now let's go back. For this one, I'll do the equation first. So which variable do they want me to use? Well, it's a different one this time. It's t, or maybe it was t last time, I forget. So f of t is, it's going to start at 1,500 gallons, and we're going to lose 3%, which means we get 0.97. And we're going to start at 0 again because a timer starts at 0, and that will just be to the t power. That means that all the equations you did in the last unit where we used an n minus 1, there was something a little bit different about how those problems were phrased. Okay, so our table is going to start with 0 and 1,500. And we'll just do a couple of these. So now we're going to take 1,500 and multiply it by 0.97. That gives us 1,455. Now we're going to take 1,455 and multiply it by 0.97, and we get 1,411.35. Not really sure we need to round that precise because, well, look at the scale. I mean, we have to get up to 1,500. We don't necessarily even want to start at 0 on our y-axis. So, for example, if we started at 1,300. And then every 5 or 4, let's go with 5. Every 5 squares, 1, 2, 3, 4, 5. There's another 100. And 1, 2, 3, 4, 5. There's another 100. When you do that, it's important to know how much each square is worth. So here's how you figure it out. If you've traveled, and I'm just going to write on here for a second. If you've traveled a distance of 100 on your scale, and you've done that in 1, 2, 3, 4, 5 squares, that means 100 divided by 5, each square is worth 20. That's a very useful calculation because that helps us to put our dots on the graph accurately. So 0 is 1,500. 1 is 1,455, which is right just barely above the line. Probably can't even see it at this scale. And then 2 is at 1,411, which is between the first and the second square. Is this a straight line? Well, the answer is no, it's not a straight line. And again, we're zoomed in too far to be able to see the curve of the function. But should we be connecting the dots together? And the answer is yes, because is the water flowing in between the minutes? Yeah, the water's continuously flowing. So it's going to come through here something like this. And we'll just put an arrow saying it's going in that direction. So for problems 5, 6, and 7, we're just going to look here and I'll say it out loud. Problems number 1 and 3 have something in common. You are not connecting the dots together. Problems 2 and 4 have something together. You are connecting the dots together. And let's see, there's some other questions here. What do we notice that's similar? What do we notice that's different? Between 1 and 3, what is different? Problem number 1 is, that's the piggy bank problem. It's increasing, but it's arithmetic. Problem number 3 is increasing, but it's geometric. And then let's see, 1 and 2, you have connect the dots, don't connect the dots. You have both of them are arithmetic. They have a constant rate of change. And then let's see, 3 and 4. What's different between 3 and 4? Well, what's the same is that they are both geometric. What's different is one is increasing, one is decreasing. And also what is different is dots are connected, dots are not connected. Now, we definitely need some vocabulary here. So let's look at our takeaways. A geometric sequence, we said that's one where you multiply. An exponential function is related to a geometric. We'll explain why in just a second. A discrete function and a continuous function. A discrete function is where the dots don't connect. And the reason we don't connect them is because there's nothing happening in between the dots. A continuous function, the dots connect. And the reason they connect is because in between there is a continuous flow. So there is a flow between the dots. Arithmetic and geometric sequences are discrete. We go from one to the next to the next. Now, geometric sequences and exponential functions, they are the same in the sense that they have the same form, they have a multiplying that's going on. The difference between the two is that exponential are continuous. You'll be able to see a continuous function because everything is connected with a smooth curve. The discrete functions, they will just be a series of dots. Well, that was the big learning for today. We're going to go ahead and stop there.